For anyone serious about database security, understanding the fundamental principles of ACID properties will give you a significant edge in securing database systems. They form the acronym ACID: Atomicity, Consistency, Isolation, and Durability. Let's explore why these properties matter for cybersecurity professionals and how their absence creates vulnerabilities that attackers can exploit. Let's begin with atomicity. This property ensures that a database transaction is treated as single indivisible unit. Either all operations within the transaction are executed successfully or none of them are. Let's see atomicity in action with our interactive demo. We have two customers trying to buy wireless headphones simultaneously. Watch what happens to each transaction step when we enable proper atomicity versus when we disable it. With proper atomicity enabled, customer A's transaction completes all three steps successfully. When customer B tries to purchase but inventory is insufficient, the entire transaction fails cleanly. No money is taken, no inventory is reduced, no incomplete orders are created. This is the all or nothing principle in action. Now watch what happens without atomicity. Customer A's payment is processed successfully, but then the system crashes before updating inventory or creating the order. The customer has been charged $50 but will receive nothing, a corrupt data state that creates both business and security problems. Attackers exploit this by targeting applications that fail to handle transaction atomically, especially during system stress or unexpected errors. For example, they might intentionally submit malformed data designed to crash one part of the process after another has succeeded. They also hunt for race conditions in applications that handle multi step operations manually instead of using the database's built in transaction controls. This can allow them to manipulate timing, causing inventory to be updated without a payment being confirmed or vice versa. Protecting atomicity is like building a security chain. If any link breaks, the entire system fails. Your database administrator sets up the transaction framework, but if a developer decides to bypass it for faster code, atomicity breaks. Your security team might catch transaction vulnerabilities during testing, but if the architect designed a flawed workflow, problems slip through. Even cloud services provide atomic transactions by default, but someone still needs to configure them properly. The second property is consistency. This ensures that a transaction can only bring the database from one valid state to another valid state, maintaining all predefined rules and constraints. Let's explore consistency with our user registration demo. We have an existing user with email john@email.com in the database. Now, two new users are trying to register with that same email address. Let's see what happens with and without proper consistency enforcement. With proper consistency enabled, the system enforces the rule that email address must be unique. Both user A and user B receive clear error messages that the email already exists. No duplicate accounts are created, maintaining data integrity and authentication security. Without consistency enforcement, both registrations succeed despite violating the uniqueness rule. Now we have three different users sharing the same email address. This creates massive authentication confusion. When someone logs in with john@email.com, which account should the system access? This opens the door to account takeover attacks and broken authentication. Attackers exploit consistency failures by targeting applications during peak load when developers have disabled certain validation checks for performance. They look for systems where business rules are only enforced at the application level, then find ways to bypass the application and access the database directly through SQL injection or API manipulation. They also exploit poorly designed validation logic that can be circumvented through unexpected input combinations or by exploiting differences between development and production environments. Your database enforces basic rules like unique emails, but attackers might overwhelm your application layer during peak traffic to bypass business logic validation. The challenge is not just setting up rules, it is ensuring that they remain effective under real world attack conditions across every layer of your system. The third property is isolation. This ensures that concurrent transactions occur independently without interference as if they were executed sequentially. Now let's examine isolation with our concert ticket booking demo. We have the last ticket for a popular concert, and the two users are trying to buy it at exactly the same moment. Both users see one ticket available when they check. Let's see what happens with different isolation levels. With proper isolation, even though both users saw the same availability information initially, the system ensures only one transaction can complete. User A successfully purchases a ticket, and user B's transaction fails cleanly when the system realizes that ticket is no longer available. No overselling occurs. Without proper isolation, both users successfully complete their purchases because each transaction sees the same outdated ticket count. The system now shows overbooked. We have sold the same ticket twice. This creates customer service nightmares and potential legal issues while also showing how attackers could exploit race conditions to bypass purchase limits or inventory controls. Attackers exploit poor isolation by targeting applications that use low isolation levels for performance reasons. They launch coordinated attacks using multiple accounts or browser sessions to create race conditions in shopping carts, reservation systems, or limited quantity promotions. They also exploit applications that read data without proper locking mechanism, allowing them to access information while it's being modified by other transactions, a phenomena known as dirty read. These attacks are particularly effective against applications that prioritize speed over security and don't implement proper concurrency controls. Isolation protection is all about finding the balance between security and speed. Finally, we have durability. This property guarantees that once a transaction is committed, it remains committed even in the event of system failure. Let's demonstrate durability using our hospital prescription system. Dr. C is prescribing medication for patient X. Watch what happens to this critical data when a power outage occurs during the prescription submission process. With proper durability, the prescription completes all three critical steps: validation, writing to permanent storage, and transaction commit confirmation. When the power outage hits, system goes offline. The committed data survives because it was properly written to non-volatile storage. After emergency power restoration, the database integrity check confirms the prescription data is intact and ready for the pharmacy. Without durability, the prescription validation succeeds, but the power outage interrupts the writing process before data reaches permanent storage. The transaction commit phase never happens. When the systems restart, the prescription is completely lost despite the doctor believing it was successfully submitted. Patient X never receives their prescribed medication because there is no record of the prescription. This demonstrates why durability isn't just about data integrity. It can have serious consequences in critical systems. A sophisticated attacker's goal is not just to breach a system, but to do so without being detected. By targeting durability, they can attack the audit trail itself. For instance, they might trigger a system disruption immediately after gaining elevated privileges. If the security logs of the event were not made durable, written permanently to disk, the system could restart with no evidence of the breach, effectively allowing for attacker to hide their tracks. Understanding ACID properties gives you crucial insight into database security fundamentals. When performing security assessments or designing secure systems, always consider how these properties are maintained and what might happen if they are compromised. These concepts are especially important as applications increasingly use distributed databases, microservices, and cloud architecture where traditional ACID properties may be relaxed for performance or scalability. In these cases, you will often encounter a different model known as BASE, basically available, soft state, and eventually consistent, which presents an entirely new set of security challenges. Remember, in cybersecurity, a strong foundation in fundamentals like ACID properties can make all the difference between a vulnerable system and a resilient one. I hope this overview helps you understand ACID properties and how they fit into your database security approach. Thank you for watching, and I'll see you in the next cybersecurity video.